Catalin, again, is another one of our grantees, and he's been really pioneering the field of lo-fi emulation. And so don't take my word for it, but do take his word for it. So please come up on stage. Thanks so much for joining.
All right, thank you. Thank you, and yeah, that was an amazing talk, Brad. I almost want to yield my time to you. I have so many questions. So yeah, so I'm a neuroscientist. I'm very interested in studying the brain as a holistic system. I'm going to tell you a little bit about my journey, and because it's a general audience, I'm going to also try to introduce what whole brain emulation is. I speak a little fast. You can take as many pictures as you want or corner me after. These are kind of the things, major things I'm going to talk about. So before I get into what is WBE, I'm going to try to tell you why I'm working on it. I'm very fascinated by free will, and I've spent 30 years plus thinking about it. And my entire AI safety agenda is around this. It's basically how is sense of agency, or the feeling that you control the world, that you're a causal agent, computer in the brain. When the heck will AGI have that? And that's probably a turning point for them, for these systems. And how do we make mind uploads or machine intelligence that experiences this? If you remember this paper from last couple of years from Bootland et al., they were consciousness and artificial intelligence. Well, my entire agenda is really figuring out this bit here at the bottom. Basically, when machines will start to have a sense of causality, probably we should worry a little bit. Now, the problem with sense of agency is widely distributed. It's a whole bunch of areas. It's probably the most difficult things to study, or one of the most difficult things to study. Schizophrenia has like 300 loci of genetic causality. They're all over the brain. So in order to get to that, you have to study the whole brain. So what is whole brain emulation? For those of you who have not had any introduction, I strongly recommend Anders and Nick's whole brain emulation map. But very one-sentence summary is the possible one-to-one modeling of the function of the human brain. What do they mean by modeling? Well, they mean a bunch of things, and you should read the paper, but it's like modeling, simulation, emulation, or reconstruction, physical, computational, otherwise. So I'm going to tell you a little bit. I thought about having fun a little bit today and telling you the types of whole brain emulation that we can have. So the classical way to think about whole brain emulation is this idea that you basically take a brain, you freeze it, or you figure out a way to maintain it, and you structurally scan it using electron microscopy, some other methods, and then you run these 4 models, these biophysical chemical simulators like the Allen Institute or the Blue Brain Project has done. This is my simulations from about 10 years ago that I did at the Allen Institute while I was working there, and you have something that looks like a neural network that's functional, that's built from a ground up on some very good mechanistic explanations or principles. The low fidelity that Alison just mentioned is a more recent idea. It's like, hey, what if we record a lot of behavior like in a mouse or like an animal, like these are gerbils that I've studied, and then we segment the data, we try to figure out what the heck the animals are doing in each stage. I'm not going to talk too much about this, but Meta is doing a fantastic job figuring out segmentation. I think they will next also figure out classification. They'll tell us at every frame what the individual organisms are doing. And we don't have to probably worry as much as a scientist about this. Probably they'll come from the field. And then we want to fit models. We want to take these behaviors, feed them into something like a language model, where instead of having words as tokens, we have like behavior states as tokens, and see how well these models do. And then we want to test learning. We want to test new environments and so on. So this is a type of mind upload. If we can capture well enough data from this organism, and we can model it well enough, probably we'll have a good copy of it. The next type of whole brain emulation is this dynamical that I'm very excited about. It's basically the goal of systems neuroscience essentially is to figure out the dynamical rules for the brain. This is a very famous plot from, I think, 30 plus years ago from Freiberg, and also Terry Szymanowski uses this a lot. It's like we want a computational neuroscience wants to figure out this entire reductionist forward model of the brain. And they forgot consciousness on there, but that's important for us. And basically, they want to know what are the mechanisms that go from molecule to cell, from cell to synapse, and so on. After 100 years, we don't have all the map filled in. It's very, very difficult. As you get to the top, we have no mechanism explanations. The exciting thing is that we're starting to put artificial neural networks. Instead of having a mechanical or closed form expression necessarily, we're starting to put artificial neural networks. So now it's exciting that we may be able to do that as well to solve neuroscience. So my approach, and I think a lot of people in this field, is to place whole brain emulation, the dynamical version, where we kind of record from animals alongside computational neuroscience. I'm probably not going to go through this slide too much. The idea is that these closed form expressions that take neural activity and explain behavior, we can just replace with a bunch of neural networks. Causality by black box networks is still there. Again, it's a bit of a technical slide, but you don't have to understand all of it. What's more exciting is that there's things beyond this now. So there's groups, including at USC and other places in the US, that have been thinking about making carbon nanotubes or synthetic brains out of them. So we go from modeling to maybe a physical reconstruction of the brain now. So you imagine you're placing all your brain cells, maybe all your brain collections with carbon nanotubes. What does that look like? That sounds interesting. We can do a whole bunch of really amazing things with these things. We can run them faster. We can probably solve all kinds of things. There's also complete cloning, right? So imagine now we're not running a computer simulation. We're just going to probably figure out a way to grow or anneal or teleport bits of tissue into your brain, or maybe copies of them. So the organoid future might get, these people work on organoids here. They might get us there. Basically, you have some kind of systems that basically reconstruct the brain. You remove all those other systems, and you have an identical clone brain. And beyond that, there's other cool stuff that we can do. We can do augmentation. I'm really super excited about that. Hopefully, I'll be around for it. But when we can go beyond just with the biologically evolved brain and achieve flourishing. What does it mean for you? I don't know. I have many ideas of what. I won't share them. There are probably some of them similar to you. Some of them are probably not as much. One big thing I wanted to really explain is that the first 3 types of whole brain animation are actually leave a lot of philosophical questions in place. The substrates, we have all this data, we put it in supercomputers, and they're going to run, they're going to give us a copy, probably like a language model. Is it conscious? Is it interpretable, etc.? It's going to be challenging. synthetic, when we start to replace neurons with synthetic things like carbon nanotubes and bucky tubes, maybe they're a little more interpretable. They look physically like, or they could look physically like organic brains. And of course, the organic version of this really has the least amount of philosophical questions. So I just wanted to leave you with that map. And then talk a little bit about my science. Again, I don't have a lot of time, but basically my goals have always been to solve free will. But to figure that out, I have to record from a lot of the brain, and I've spent a lot of my time trying to figure out how to record at least from substantial parts of the whole mammalian brain. I was at the Catalin Institute for a bunch of years. I was actually writing Fortran code to do simulations and extract electrophysiological signal. And I empirically showed, and nobody cared at the time, but increasingly this is more relevant, that if you can place electrodes about 50 to 100 microns apart in the brain, you can record from basically 100% of the spikes in the brain. So, thanks to Foresight, I'm pursuing this now. Thank you. I'm building basically the world's most advanced behavior cages, cheap loggers, etc., and to build these things. This is not a video of my experiments. This is just naturally behaving gerbils in a little zoo setup. And my goal really is to record from all 400 cubic millimeters. I gave this brief talk last night of the mouse brain. And I got this little silly video, which is like, you can zoom in, and basically if this animal's running around and you somehow have access to all these 400-ish cubic millimeters in some version, you can probably create an emulator. We're starting up. I've been building for a few months. We're starting to get great small victories. Some victories are bigger. We're already synchronizing our systems to near microsecond resolution. This is my last slide. I'd like to turn whole brain animation into a science. And what does that look like? Well, it looks like, for example, the functional stuff that I do, I have an animal, I record from it, and I try to create this model, this little digital model. And the structural people they don't have a behavior access, but they're also doing something very similar. They're building they're scanning the brain and building these forward models. What if we can share data? What if after I do my month-long or year-long experiments, I have an animal that's been alive, most animals live for a few weeks, but our animals can live a year or longer. I share those brains, and those are the brains that get scanned. What happens when you build up forward models? Can we test them against the real data? And can we test the WE modality? So that's it. Thank you so much. Looking forward to talking offline.
Thanks. Oh, many hands are going up. Nico.
So in the 80s, there's Rodney Douglas that went with the canonical circuit. They did 1 millimeter cube, they mapped the local circuitry, and then there was lots of dark matter, lots of synapses that they didn't know where they come from. How are you solving that?
It's a very good question. So I think Conrad's going to talk about causality. So I'm less interested in causality, to be perfectly honest. I'm interested in modeling. So if you read my preprint, it talks about moving one of the goals of science from mechanistic explanation to explanatory, to prediction, excuse me, so that we can actually do things with things. Like of course we want mechanistic explanation. That's a very important thing for the human mind. We've evolved to have mechanistic explanations, and that's how we make progress. But the idea is that if you have things like universal approximation theorem, if you have enough data and enough dynamics, you probably can extract the manifolds on which the most interesting things to us lie. At some point, we're not going to be able to tell the difference. If language models get really, really, really good, they're embedded in a little robot, our little minds are probably not going to be able to tell the difference beyond. And this is now getting closer to the AI alignment problem. And what does that mean really to not be able to tell the difference? So the dark matter may just not matter, or it might matter for us from a utilitarian or utility point of view.